All right, here we have um, activity 2.1.7. It's number 4, and there's also a number 5 that we'll do another video on here shortly. But 1 through 3 on the activity was just more like static determinacy, that kind of thing. So this is our first kind of smaller truss for the problems, and like any truss, this one's a little different, but like any truss, we start with that 5-step process, and drawing our free body diagram is step 1. So the difference in this problem is simply the fact that we have our supports on the vertical. So typically we draw them where they're horizontal, parallel to each other on the horizontal, but it doesn't change a whole lot. It just changes where we draw our reaction forces. So step 1, we're going to draw this free body diagram. So that's going to go a little something like this. And we'll label our joint C, B, A. And now as we look at this, and you can add the 3 feet, the dimensions if you'd like. For this video, I'm just going to skip ahead. But we need to write out all of those external forces, and we immediately see we have external force at C in the vertical of 50 pounds. Next thing we see, we have our pin and our roller joint. So our pin up here at B, pins always have 2 reaction forces. Now, I can choose to draw that arrow either pointing to the right or the left. Looking ahead, I know that whatever I draw for B, I want to draw the opposite at A, because in the end, when we do the summation of forces, we want these to balance out to 0. So as I do that, though, I'm going to also specifically choose B to point to the left. And we're going to call that the reaction at B in the X direction. The reason I choose that to the left is natural tendency. If I imagine the 50 pounds is pulling down, that's going to want to pull this joint B away from the wall, let's say, that we're mounted to. So because it's trying to pull away from the wall, the reaction force is going to be towards the wall to counteract it. So just a simple guess. We might be right, we might be wrong, but using the common sense approach, I'm going to point that to the left. And again, like I mentioned, I'm going to point this one to the right to counteract it, reaction A in the X. And the roller at A means we don't have a vertical reaction at A, but we do have a vertical reaction at B. And again, using this common sense approach, looking ahead, the 50 pounds is pointed down. So when we sum our forces, we need to have something to counteract it. So I'm going to choose to draw that arrow up. So with all of that said, that's going to be our free body diagram. So that's step 1. Step 2 is going to be drawing out our sum of our moment. And in the handout I gave you guys in class, I had mentioned typically we do that sum of the moments from the pin joint. So in this case, we're going to do that from B. We know that the moment, the rotating forces, always sum to 0. We don't want this thing moving. So what moments are created in this problem? Well, at B, we have a moment created by the 50-pound force. So using our right-hand rule, wrapping our thumb, pointing the thumb in the direction such that our fingers curl the rotation direction. So what I'm saying is put your thumb at B, and I need to curl my fingers in a clockwise position. That means my thumb is pointed away from me, and that means that our moment there at C is negative 50 pounds times the distance perpendicular. Well, in this case, it happens to be 3 in both directions, but it would be this horizontal distance 3. So 50 times 3. The other moment we have from B is actually going to be from the reaction force A in the x direction. So the moment here is positive, which is good, and it balances out. But if we put our thumb at B and curl our fingers in a counterclockwise position to represent that moment caused by RAX, that is a positive moment. And the force we don't know. That's R at A in the x direction, so RAX, times its distance from the fulcrum, which is, in this case, joint B. And that is also 3 feet. So if we look at this, we have one equation, we have one unknown, so we get 0 is equal to negative 150. Whoop. Whoop. Let's try and fix that. Now, the algebra is simple enough here that you can see that we've, if we move our 150, let me just finish this out just to show this first time through. We add 150 to both sides, so 150 itself is RAX times 3. See, and then we get divide by 3, RAX is equal to just 50. So if you were to look at it from the first line here, we've got a 50 and a 3, and then we have a variable and a 3. So looking at the algebra, we could have kind of looked at that and said, well, RAX has to be 50. Positive versus negative, that'd be nice to run the numbers. But so we did choose RAX to be the correct direction because our number ended positive. Remember, anytime we answer with a negative, we've just simply guessed the direction of the force to be the opposite. So if we create our table, we want to, maybe I'll change the settings here. Hopefully green is still visible here. Geez, okay. So we're going to kind of have this table because as we quote unquote solve a truss, we're really looking to find all these mythical forces that we don't have at the beginning. So one of those being RAX. We just found that to be 50. Now, I have not been using units. It's a little tough on this writing on my laptop screen. So I should have been using units throughout here. But in this case, the force RAX is 50 pounds. We still have external force RB in the X, and we also have RB in the Y direction. We don't know that either. While we're at it, I guess by definition, we're looking for external forces, and we do have that external force C in the Y direction. That is an applied load, so we already know that that's 50 pounds. So we've done step 1, free body diagram. Step 2, we did some of the moments. I don't know if it's 3 or 4. I don't know where we're at here exactly, I guess, in that step-by-step handout I gave you guys. But when we go to do the sum of the forces, we can choose either sum of the forces in the X or the Y. Typically, it ends up being in the Y direction. Here we can choose either one. But for now, let's see. Let's do in the Y direction. So sum of the forces in the Y direction. Same thing, they sum to 0 because we don't want this truss moving. So what forces do we have in the Y direction? We have the FC in the Y, that applied load negative 50. And we also, the only other one would be, oh, I'm sorry, I did not label that. RB in the Y direction. So negative 50 because it's pointed down. And then we have plus RB in the Y direction. Well, when you look at that, that's pretty simple to solve. We add 50 to both sides. 50 equals R of B in the Y direction. So we've solved RB in the y direction. And you can do this at any time. You don't have to stop your progress. RB in the y is also 50. Okay. And then we go back and we say, well, the only thing we haven't done here is solved the sum of the forces in the x direction. Well, same thing. We don't want this thing sliding side to side, so we sum those forces and we get 0. Right now we only have, well, we have RA in the x. We have pointed that to the right, and we were correct in our guess based on that. And then we also have RB in the x. So 0 is equal to RAX, which we found to be positive 50, minus RB in the x. Again, similar to the Fy, we find that 50 is RB in the x. So we change that, green, and we find that every single force in the externals are 50 pounds everywhere. 50, 50, 50, 50. We do have the arrows pointed correctly. We did assume all that correct. So with that, I'm going to pause this video. That is external loads for 2.1.7, problem number 4.